Before we start about machine learning, we want to start with a very serious story. A story about a gnome. This is Norman. He lives in the forest, waters plants, vibes with the rabbits. Premium Forest main character energy. Norman is a wholesome person. He waters flowers, talks to squirrels, emotionally supports the butterflies, but deep down, he's kind of lonely. So one day, he goes for a stroll hoping to make a friend. On his walk, he meets a snail. But not just any snail. This snail looks like it just failed its midterms and is questioning every decision they've ever made. Norman, being the kind legend he is, takes care of the snail, feeds it, and they become friends. So Norman brings the snail home and decide to watch a movie together. Wholesome bonding time. As Norman went to grab a soda for them, the snail says, "Hold on, let me pull up GoodReads review for this movie, just to check if it's good." He opens the review, and the first sentence is a massive spoiler. Like, it just straight up reveals the entire thing.
It was at this moment that he knew. He fucked up.
And Norman absolutely loses it. He looks at the snail like, "Bro, you ruined the entire movie. We haven't even started." Snail tries to defend himself, saying, "I didn't know. GoodReads betrayed me." They argue, the fight escalates, a mushroom gets thrown, and just like that, Norman loses his only friend. All because of a spoiler.
Emotional, damn it!
So comedy aside, this is like the main problem we're trying to solve right now. Spoilers in movies and books can ruin the entire experience, just like they ruined Norman's night and his one friendship.
Okay. Enough about Norman's emotional roller coaster. Before you call the snail again, we should actually explain what we're predicting. So, here's the real task. GoodReads only gives a review level spoiler tag, basically a giant warning slapped on the whole review. But inside a review, you get harmless sentences like, "The pacing was slow," right next to the ones that ruin the entire plot, like the main character dies eventually. So, what we want is simple. We take one sentence at a time and predict whether that sentence is a spoiler or not. Just a clean yes or no classification. Now, evaluating this is not a straightforward task because the data is super skewed. Only around 8 to 12% of the sentences are spoilers. So accuracy, totally useless. A model could predict non-spoiler for everything and get an 88% accuracy score and be just as helpful as, well, the snail-picking movies. So instead, we focus on F1 score for spoilers because that tells us how we're actually catching them. We also look at macro F1 to keep things fair across both classes, but spoiler F1 is the main metric. Before using fancy models, we start with a simple baseline. First, the majority baseline. Always predict non-spoilers. Then a basic keyword check if it has words like dies or endings and then just flag it. Finally, our real implemented baseline, bag of words and logistic regression. It's simple, fast, and gives us a good starting point. And to keep our evaluations honest, we split the dataset by review, not by sentence, so nothing leaks across splits. Every model, SVM, LightGBM, SBERT, Distilbert uses the exact same train, valuation, and test sets. Alright, now that the actual task is clear, now you can bring the snail back. You remember the snail? The one who looked like he failed all his midterms? Yeah, he's back. And he's going to walk you through the data streaming, cleaning, and the 1.3 GoodReads review that we had to deal with.
Right. Now that we have recovered from Norman's emotional damage, let's snap out of the story and look at the real data problem we're solving. I'll walk through step 2, which covers our exploratory analysis, data streaming, pre-processing, and how we prepare a dataset for modeling. We start with the raw file you saw in the notebook, GoodReads reviews spoiler.json.gz. It's a part of UCSD's GoodReads book graph, and this file is huge, about 1.3 million reviews, and each review contains a list of sentences stored as review sentences, along with a review level spoiler label called hasSpoiler. Because this file is too large to load in memory, we use streaming, reading 50,000 reviews at a time. The streaming pass gives us our first high-level stats. As you can see, the total reviews we processed were around 1.3 million. The reviews with spoilers are around 89,000, and that's only 6.5% spoiler tagged reviews. And reviews vary a lot in length as well, anywhere from 1 to 50 plus sentences. As you can see on the histogram, where most reviews fall in the 2 to 10 sentence range, but there's a long tail. This variability is the reason we convert everything to the sentence level instead of working at the review level. While streaming, we sample exactly 100,000 reviews out of the 1.3 million to keep things tractable. After expanding these reviews into sentences, we end up with 1.24 million sentences. Next, we apply weak supervision. If a review is marked as containing a spoiler, we label all of its sentences as spoilers. Otherwise, they all become non-spoilers. This gives us a workable sentence-level dataset, even though GoodReads doesn't provide sentence-level annotations. Once we have the sentences, we run some light cleaning. We lowercase, strip white space, and remove extremely short sentences. Things like okay or may, as step review removes around 78,000 sentences, leaving us with 1.16 million usable sentences. Now, one of the most important findings shows up in the class balance plot. Out of the 1.16 million sentences, Looks like around 1.099 million are non-spoilers and around 145,000 are spoilers. That's only 88% non-spoilers and only 12% spoilers. This imbalance is exactly why accuracy is not meaningful for this task. To prevent the train test leakage, we split at the review level, not at the sentence level. The split shown gives us 117,000 training sentences, 175,000 validation, and 175,000 test. And then all of step 2 is complete. After doing all these n-gram and interpreting the n-gram, we pre-process the text. We package the clean dataset into a single paraquet file. This is the file named process_sentences.paraquet shown on pages here. And paraquet version keeps only the clean sentence, the label, and the split, shrinking the data to about 75 MB while keeping everything necessary for modeling. This file is what the modeling team uses in step 3, and it avoids the need for anyone to restream or reprocess the massive raw dataset. However, because our original dataset was so imbalanced, modeling on it directly would heavily favor the non-spoiler class. That's why right before modeling, we apply a 50-50 balancing step. That happens here. We undersample the non-spoilers to match number of spoiler sentences. This gives us a balanced dataset of around 271,848 sentences, and this is what Sachin will build the models on.
Right, then let's move on to talking about the model. Since it's going to be pretty long, I have Subway Surfers on the side for you guys to, learn it the Gen Z way. Yeah, let's get started. We're going to be walking through the modeling approach for detecting spoilers in GoodReads book reviews, as we talked about. And the challenge here is that instead of just checking if the review is a spoiler or not, we're going to be doing a sentence level classification where we identify whether a given sentence contains the spoiler or not. So how did we formulate this as an ML problem? How we formulated this is that we have inputs, which is the clean review sentences as text, and we have outputs, which is the binary classification if that particular sentence is a spoiler or not. And what we're optimizing for here is the F1 score on the spoiler class specifically. Why? Because in the real world, missing a spoiler, which is a false negative, is much worse than incorrectly flagging a non-spoiler. We don't want to ruin someone's reading experience, but it's alright if it makes some mistakes where it classifies, a non-spoiler as a spoiler, because that wouldn't ruin someone's reading experience. But we also track the macro F1 to ensure that the balance performance is across both classes, but spoiler F1 is our main metric here. Moving on, let's get started on the notebook here. We see that we're going to be using the GPU to run this because this takes hours to run and it would take much longer if we didn't have GPU available, so we just set that up here. And here I've set up some code to add checkpoints such that if our code suddenly stops in between or you want to rerun some cells, you don't have to rerun every cell that's before it. We store the model checkpoints in pickle files, which is archived and in a way that it doesn't take up too much space. So if it's already detected, it will just load up the full data set and any models that we've previously found. The first thing that we do is balance the data set, because our initial input data set is highly skewed towards non-spoilers. Over, I think, 89% of our input data set was non-spoiler data, and training it on this data would cause the model to learn bad characteristics that won't generalize well. So we're first splitting it, we're undersampling the datasets such that we have a more equal distribution of spoilers and non-spoilers. And here we can see that the balance is almost 50-50 after we perform this. We then prepare the data for modeling by splitting it into training, validation, and testing. And we can see the splits here as 0.3 and 0.5. Moving on, we first train our baseline model. So this is a pretty simple baseline model. It uses logistic regression with bag of words features. We can see that we're using count vectorizer with 5,000 max features, and it's going to remove the stop words in English from these, and it gives us a quick sanity check and establishes a performance floor for our remaining models. It's fast and interpretable because we can exactly see the words that it's training on, but it's pretty limited because it just treats the text as counts of words, but it doesn't understand the order of the words in the sentences or the semantics of it. Moving on, we come up with our first model here, which uses SBERT embeddings. Over here, we're creating a 768 dimension dense semantic embeddings, and these embeddings capture meaning and context better than just a bag of words representation. We also engineered linguistic features, things like position in the review, sentence length, and punctuation density, etc. So you can see that here we're creating the embeddings, and here we're doing the feature embedding where we have a list of spoiler keywords. We figure out the position of the word in the sentence. We check if that sentence is in the first third of the review, is in the last third of the review. We check about for temporal words, which is like finally, eventually, words relating to time. We look for the length of it. We check if that sentence has quotation marks, has questions, has exclamations, and we append all of this to these SBERT embeddings in order to create a rich hybrid representation of features for each sentence. So now that we've done all this processing to give the model more and more details, we can move on to creating our different models. So now we see that we have a bunch of different models that we can use now that we have all of this. Our first model is going to be using these SBERT embeddings and the features along with light GBM. Then we have a linear S support vector machine model on the combined features, and we also have a DistilBERT fine-tuning model. Let's walk through each of these step by step. First up, the light GBM model over here with GPU acceleration. It's essentially a gradient boosting model that builds an ensemble of decision trees. Why did we pick light GBM? It's because it's super fast to run. It trains pretty fast. I think it took about maybe 15-20 minutes on our GPU. It handles about 768 expert dimensions, and we used 500 estimators with a learning rate of 0.05 and a max depth of 10, as you can see here. The advantages we had of this model is that it's really fast in training and inference, and it's good with high dimensional data, and it captures feature interactions. And we get some interpretability because we can see which features were most important in the final model. But the disadvantages is that it still relies on the frozen SBERT embeddings, and it can't learn to adapt those representations specifically for spoiler detection. You can see where we trained this model and details about its accuracy, which we'll come back to later. We can also see the linear SVM model here, which finds a maximum margin hyperplane in our high dimensional feature space. We use the C value of 1 here, through testing to figure out what works best for our model using validation sets. And I think this is pretty computationally efficient too for like large data sets, and we were able to train it pretty quick. The main disadvantages here is that because it's a linear model, it can't capture complex non-linear patterns, and this might lose some details. And it also again uses the frozen SBERT embedding, so it can't do anything task specific. This is us training it, and we'll come back to the accuracy. Our final model is the distilled BERT fine-tuning model. This is our most sophisticated model, and it used a distilled version of BERT with 66 million parameters. Unlike our previous models, this doesn't use those frozen embeddings. Instead, we fine-tune the entire transformer end to end, and we allow it to learn task-specific representations that are optimized specifically for spoiler detection. The advantages we have here is that it can actually understand language, it can capture subtle contextual cues, and have a long range of dependencies, and it can really understand how words earlier on can connect with words later on, and it can learn those patterns really well. It learns these from scratch, so it's really good for our specific task. The main disadvantage here is it takes much longer to train. Even with the GPU, it took multiple hours. And it's also a complete black box in terms of interpretability, so we can't really understand why it took a certain decision of whether something's a spoiler or not, and there's a risk of overfitting. We implemented this using Hugging Face transformers and learning rate of 2e to the -5, and we trained for 3 epochs in total. Let's go on to the final results and understanding how well our models did. In talking about the evaluation, I'm going to cover 3 key areas. First up, I'm going to justify our evaluation metrics and why they're appropriate for this task. Then I'm going to move on to establishing our baseline and demonstrating our improvements from the baseline. Then I'll walk through the implementation, and we'll have some statistics and visualizations. Understanding how our spoiler detection should be evaluated. In the real world, like GoodReads data which we used, spoilers represent only 8 to 9% of sentences. The main issue because of this is that accuracy is super misleading, because a naive model that predicts non-spoiler for everything can achieve 91% accuracy, but it's completely useless because it might just never predict. And plus, the costs of errors are asymmetric. Missing a spoiler, which is a false negative, directly harms the user experience by ruining their reading experience. But a false positive, flagging a non-spoiler, just causes minor annoyance. So we want to really focus on preventing those false negatives over minimizing the false positives here. So why did we choose F1 score on the spoiler class as our primary metric? It balances both precision and recall on the minority spoiler class, which is what we actually care about. The precision is what measures how much flagged spoilers are real, and the recall is what measures how many actual spoilers we catch, which is critical for protection. The F1 score, averages both of these and ensures that you don't optimize one at the expense of other. Accuracy would ignore this class imbalance and treat both errors equally, and the micro F1 would be dominated by the majority class. We do use macro F1 to ensure that it's a balanced performance across both classes, but spoiler F1 is our main metric. We also use ROC AUC and PR AUC because these are more informative, and it focuses on the precision recall trade-offs without the large true negative region inflating the scores. And let's go on and talk about the baselines here. The simplest baseline, as we can see in this image here, is always just predicting non-spoiler because that's the majority of our data, and the spoiler F1 performance of that would be 0. Our bag of words logistic regression here is able to achieve 0.74 spoiler, and we can see that the linear SVM, light GBM, and distilled BERT models that we have achieve huge gains on this. Our distilled BERT can achieve over 16 to 17% relative gain over the bag of words baseline model that we have. Going on to our code here, which evaluates our model, we see that what our code does is essentially load these models which have been saved, as we saw when generating these models, and it essentially creates the predictions based on these, and it's able to evaluate these based on the scores that we have. Now, looking at our model performance comparison here, we can really see that all of our models dramatically outperform the trivial baseline, and most of them are significantly better, like a 16-17% improvement from the baseline bag of words representation model that we have here. You can see that particularly looking at the spoiler F1 score with our Distilbert model, it's a whole 10%, 0.1 higher than the other models here. We see that even though the linear SVC and the light GBM model overcome the bag of words model because they're more complex and understand the data more, the Distilbert model is just way better just because of how much it learns, how long it trained for, and the different features that it has. We can move on and look at more metrics here. We can see that the improvement over the baseline 16%, as we said before. Moving on to the confusion matrices, now we can really see why our Distilbert model shines over the rest. We see that the baseline model particularly has these false negatives here, where the true label is a spoiler, but the predicted label is non-spoiler. Now this is what we want to avoid, where spoilers are misaccurately labeled. We see that our Distilbert model gets this down to just 20%. So just 20% of spoilers are mislabeled, as opposed to 44% and 40 and 40% of our other two models that we trained. But we see that the trade-off here is we have a higher rate over here, where non-spoilers are predicted as spoilers. We see that this rises to 61% over 40%, but here we believe that this is a trade-off to be made, because this issue is way more important than this issue right here. But we see that most of the labels are correctly labeled here, which is shown in the fact that the diagonals are always a darker shade, which means they're always more accurate in this case. Moving on to the curves here, we can see that the precision recall curve over here shows that the blue model, the baseline, is down here, and we see that our models and the Distilbert model particularly perform way higher than those on average. And we again see here that the baseline is closer to the center line, but our Distilbert model, linear model, and light GBM model do perform much better, as in they're more curved over here. Moving on to the feature importance analysis, we can see that in the light GBM, it did not really use the features that we added here of temporal count, hash question, hash exclamation, these features that we manually used. Interestingly, it used the SBERT features, the semantic analysis features, way more in its deterministic things. But here we see that the engineered features, we can see what features were used the most here. Looking at this model, we see that the length of the sentence, the position of the sentence in the review, whether the sentence has quotation marks or not, if the sentence has spoiler keywords as we define them, and if the sentence is in the last third of the review, had the most importance in figuring out whether it was a spoiler or not for the model. Looking at the error analysis, we see that, interestingly, these are non-spoilers incorrectly flagged as spoilers, but reading through this, honestly, I think most of them are spoilers. So I think this might just come down to inaccuracies in our initial data set that was provided. Over here it says, specifically when he asked Daisy out at the tail end of book 1. This is very clearly a spoiler, but apparently this was labeled in the original dataset as a non-spoiler. So we believe that this might also be contributing to lower, F1 and precision and recall scores, and a real score might be really higher if all of the records were correctly labeled. Again, looking at the false negatives, these were supposedly actual spoilers that were missed, but we see that most of these aren't really spoilers. There's no real information given in here. So, if you look past all these issues in the initial data set, our model probably likely performs better given perfect data. But of course, perfect data is very hard to achieve. These are some more stats on the performance by sentence length and keyword presence, and we see that the model does really well. The more longer the sentence is, it's able to achieve 76% F1, but on short sentences, as they get shorter and shorter, the F1 score really goes down on all models equally. And of course, models with the keywords perform much better than the models without keywords that indicate spoilers. So I'd say our model did pretty well. It performed way better than the baseline, and it's able to almost always identify spoilers correctly. Although the small drawback is that sometimes non-spoilers get marked as spoilers, but again, this is a much smaller problem as we talked about. So we're pretty satisfied with the results here.
For our literature review, we looked at how spoiler detection has been studied across different datasets, modeling approaches, and learning paradigms. We start with the GoodReads spoiler dataset introduced by Won et al. In 2019, which is still the largest and the most influential resource in this area. They show two major challenges. Spoilers are extremely sparse, and true sentence level labels are expensive to collect. Even in their work, only a small subset of sentences is human annotated. Models trained on this subset show a clear trend. Transformer-based classifiers like BERT reach sentence-level F1 scores around 0.63 to 0.71, while classical models like logistic regression or SVM struggled around 0.2 to 0.3 range. This establishes the big performance gap between surface-level lexical features and contextual reasoning. We also examined other datasets historically used for spoiler tasks. IMDb movie reviews rely on reviewer-marked spoiler sections but operate at the document level. EV Troops is stylistically rich, but not aligned at the sentence level. Amazon book reviews don't include explicit spoiler labels at all. Compared to these, GoodReads remains unique. It's large, fine-grained, and provides natural sentence boundaries, which makes it the most suitable foundation for sentence-level analysis. In terms of modeling, the literature falls into several families. Transformer models dominate because they capture narrative cues that keyword-based or syntax-based systems miss. Genre-aware methods help when metadata is available. Syntax and dependency-based models try to infer narrative structure, but they often underperform contextual models. And finally, noise-aware learning, including distance supervision and label denoising techniques, directly motivates our use of weak supervision and hard negative mining. Together, these papers show that spoiler detection is fundamentally a contextual, imbalanced, and noisy label problem. That's why our project brings these ideas together. We generate large-scale weak labels, clean them using hard negative mining and the benchmark between both the classical and transformer-based models to understand how each family handles spoiler sparsity and narrative complexity. Despite having only noisy review level labels, we built a large sentence level spoiler dataset using weak supervision, cleaned it with hard negative mining, and benchmarked multiple models. Our results show that contextual transformers like Distilbert significantly outperform classical baselines, demonstrating that fine-grained spoiler detection is possible even without manual annotations. Thank you.